In this video, I'm going to talk about reference and indicator electrodes and also a little bit about junction potential and what that is, and also how that affects electrochemical measurements. So let's start off with the junction potential. And what that is a small voltage that develops at the end of a salt bridge. So remember, in the last section, we're talking about voltaic cells, and connecting each of the voltaic half cells is a salt bridge. And what that does is it allows cations and anions to flow to each of the half cells and basically balance the charge that is being moved around that voltaic cell. So if we remember, the electrons in a voltaic cell will travel from the anode to the cathode. So as written, they would travel from left to right on the diagram. So the left side of the voltaic cell is going to be losing negative charge as the electrons are flowing away. So that negative charge has to be replaced by another negative charge, and in the case of the salt bridge, that means that the negative anions in the salt bridge will be moving into that left-hand half cell, or the anode, and it's called the anode because anions flow towards that particular electrode. Now on the other side of the half cell, we have the cathode, and cations are going to be flowing that way because we're going to be having excess negative charge building up on that half of the voltaic cell, which means that we have to balance out that negative charge by adding some positive charge. So cations from the salt bridge will be flowing into that half cell to balance that reaction. So because ions are flowing within the salt bridge, ions don't all flow at the same rate. Some flow faster than others, and because of this difference in speed at which they flow, the difference in their mobilities, so this is a fundamental limitation on the accuracy of direct potentiometric measurements, because we don't know how much of the voltage that we're reading is due to this junction potential. In most cases, it's probably just a small amount, but since we don't know what it is, we can't really account for it. So since the junction potential occurs at the end of the salt bridge, we need to have the salt bridge made out of something that is going to minimize that junction potential. So we have to have ions that flow at about the same rate. So if we had a salt bridge that was made of sodium chloride, chloride diffuses faster than sodium, so that is going to create a junction potential. But if instead we made it out of potassium chloride, the mobilities of potassium chloride are fairly equal, so that is going to minimize the junction potential if we use potassium chloride as the salt bridge. And because their mobilities are about the same, most salt bridges are made of KCl. So here's an example of what might happen at a junction and how the junction potentials are formed. So if we have in diagram A 0.1 molar HCl on the left-hand side and 0.01 molar HCl on the right-hand side. And in between each of those two solutions is a membrane that only allows ions to flow through it. So in this case, since the 0.1 molar HCl side is more concentrated than the 0.01 molar HCl, the ions are going to want to flow from left to right. But since the H plus ions travel much faster than the Cl minus ions, what's going to happen is the H plus is going to build up more quickly on the right-hand side of that diagram, which will result in this positive charge building up on the right-hand side of the membrane. And since Cl is not as quick to flow through that membrane, there will be a negative charge that builds up on the left-hand side of that membrane. So that difference in charge, due to those ion mobilities being different, is the junction potential. So here's a table showing the different ion mobilities in water. And if we look at potassium, which is here, and chlorine, which is right here, you can see that their ion mobilities are pretty close together. Okay, they're not going to be the same, but they're fairly equal. If we were to look at sodium, which is a little bit farther down on the table, you can see that the mobility of sodium is much lower than that of potassium. So it is not a good idea to make a salt bridge out of sodium chloride because the mobilities between sodium and chloride are quite different. Now you might be wondering what determines the mobility of an ion in water. So maybe pause the video and look at the numbers and see if you can try and figure out why, for example, potassium would be faster than sodium, or NH4 plus would be a little bit faster than lanthanum 3 plus. and see if you can figure out if there's any kind of pattern in these numbers. You may have thought that it had to do with how small an ion is, or whether or not it's a complex ion or not, and that doesn't quite work if you look at some of the ions in this chart. So for example, we have fluorine, which is pretty slow, and it's just a very small ion, and whereas we have something like sulfate, 2-, which is a lot faster, even though it is a larger ion. So it doesn't really have to do with size. It doesn't have to do with charge. What it does have to do with is something that is not really on this chart at all, and that's what is called the hydration sphere. So you learned about this briefly in general chemistry too, and you can think of it as a bunch of water molecules that are attracted to each of these ions. And the more water that's attracted to these ions, the more water it has to drag with it as it's migrating through the solution. So let's just do a quick example. Using the table on the previous slide, determine which side of the junction will become positive and which side will become negative, assuming equal concentrations of each component. Okay, so if we have equal concentrations of each component, we notice right away that we have sodium on both sides of the membrane, right? The membrane being right there. So if we have sodium in each side of the membrane and it's at equal concentrations, there's going to be no net flow of sodium across that membrane. So the only things we have to worry about are the nitrate and the chlorine. So if we go back to the previous slide, we look at chloride and we look at nitrate, and we can see that chloride has a higher mobility than nitrate does. So what will happen in this diagram is that the chloride will be moving towards the left and the nitrate will be moving towards the right, but it won't be moving as quickly as the chlorine is moving. So since the chloride is moving faster to the left, we'll have an excess negative charge building up on the left-hand side of that membrane. And since the nitrate can't move fast enough to replace those negative charges that are being lost by the right-hand side, then the right-hand side is going to have an excess positive charge associated with it. So now let's talk a little bit about electrodes, and more specifically reference electrodes. But I also want to mention indicator electrodes. So an indicator electrode is the electrode that responds to the analyte. So for example, when you are measuring pH, pH is actually an electrode that responds to the H+ concentration, and then that concentration is converted into a voltage, and then the voltage is converted into a pH that you would read on the pH probe. Now, a reference electrode is another electrode that also has to be present when you're doing an electrochemical measurement, and the reference electrode maintains a fixed reference potential. So all potentials that you measure, all voltages that are measured with an electrode, are measured with respect to the reference electrode. So the reference electrode will have a specific voltage associated with it, and then the indicator electrode will have a voltage that is different than the reference electrode, and that difference is going to tell you what the concentration of the analyte is in the particular solution that you are measuring. Now, when we're writing cell diagrams, line diagrams, or a pictorial diagram of a voltaic cell that includes a reference electrode, by convention, the reference electrode is always on the left. So if we had a reference electrode here, this happens to be the standard hydrogen electrode that we will talk about shortly. That has a fixed potential, and if we put some analyte or some other half cell on the right-hand side of this voltaic cell, the voltage is going to only depend on what is in the half cell that is on the right of that diagram. So whatever we put there, we put a silver solution, a zinc solution, a nickel solution at a different concentration, that voltage change will only be associated with what is on the other side of that voltaic cell. So the standard hydrogen electrode, or She, is an electrode that is made out of 1 molar hydrochloric acid and 1 bar of hydrogen gas. And it's a standard hydrogen electrode because of the concentrations being 1 molar and the pressures being 1 bar. So since the standard hydrogen electrode is a reference electrode, it'll be on the left-hand side of the diagram, and the reaction of interest is going to be on the right, and in this case, that's a silver solution with a silver electrode. So then when we hook this up all together and we get a voltage that is shown on the potentiometer or the voltmeter that is hooked up between these two half cells, the voltage that we see there is going to be the voltage that is associated with the particular analyte of interest. So when you're looking up standard reduction potentials in Appendix 13 of your textbook, the values that you see are the difference between the standard potential of the reaction of interest and the potential of the standard hydrogen electrode. And the potential of the standard hydrogen electrode is by definition 0 volts. So whatever voltage we get from the voltmeter is going to be the voltage of that particular half cell that we are interested in. So one thing to notice about the standard hydrogen electrode is that it has a platinum electrode and it has an input of hydrogen gas around that platinum electrode. And here is the acid solution that it is all immersed in. So the platinum electrode in this case is not really participating in the reaction itself. If you go back to the previous slide, you see the reaction for the standard hydrogen electrode involves H+ and hydrogen gas. There's no platinum in there at all. So the platinum in the standard hydrogen electrode is only there to exchange electrons. So in the case of this particular voltaic cell, the electrons are moving from the platinum electrode to the silver electrode. Okay, it could move the other way. If it was zinc on the right-hand side of this diagram instead, we'd have a voltage of minus 0.762 volts, and a negative voltage would mean that the electrons are traveling from right to left in this particular diagram. So again, when doing these measurements, we're always going to place a reference electrode on the left-hand side of the cell diagram, and the half reaction of interest is always going to go on the right. If the electrons flow from the standard hydrogen electrode to the reaction of interest, the standard reduction potential is going to be positive, just like on the previous slide. And as I was mentioning before, if electrons flow to the standard hydrogen electrode from the reaction of interest, the standard reduction potential is going to be negative. So we don't normally use the standard hydrogen electrode when we are taking electrochemical measurements. We'll usually use one of two electrodes, and the first one I'll talk about here just briefly is called the calomel electrode. And this is the reaction of the calomel electrode. So it's mercury chloride in equilibrium with mercury and chloride, and the mercury chloride is called the calomel. Now this doesn't have a voltage of 0 volts like the standard hydrogen electrode. It has a voltage of 0.268 volts in its standard conditions, but usually with these types of electrodes, we don't use them in their standard state conditions. We don't use 1 molar KCl, for example. We use a saturated KCl solution. And that's just to make sure that the KCl in this electrode is not changing concentration, because we want to make sure that the voltage of this particular reference electrode remains constant. And the way to do that is to make sure that none of the components in there are changing concentrations. So usually we use a saturated calomel electrode where the KCl within the electrode is saturated. So that's this light gray stuff in the electrode diagram over here. Now you can see they don't quite look as rudimentary as just a beaker with a metal electrode and a salt bridge in it. These are things that are much more compact and that you would purchase from a company and use in your particular application. So you can think of this as one of the half cells of a full voltaic cell, and the salt bridge is built into these, which is right at the bottom there. So this would just be immersed in the solution of interest as a reference electrode, and then you'd have to have another electrode that it would be connected to in order to make a measurement of a particular analyte. So I'm not going to be worried about the details of how this particular electrode and the next one are put together. I just want to let you know that they do exist and that they are much more useful than the standard hydrogen electrode, which we'll talk about again in just a second. So another electrode that is commonly used is called the silver-silver chloride electrode. So silver chloride going to silver solid and chloride minus. And again, the standard reduction potential is 0.222 volts, but since we want to make sure none of the concentrations of the components change, we usually use a saturated KCl solution in this one as well. So the voltage for that one is 0.197 volts. And just like the previous diagram, the saturated KCl is this gray stuff right in the diagram. So again, this is just another electrode that is nice and compact. You could think of it as another part of a voltaic cell, one of the half reactions that is going to allow a reaction or a voltage to flow if this is hooked up to another electrode and immersed in a solution. So we've looked at 3 different reference electrodes: the standard hydrogen electrode, the calomel electrode, and the silver-silver chloride electrode. So why would we use, for example, the silver-silver chloride electrode or the calomel electrode and not the standard hydrogen electrode when doing a measurement? Now the simple answer is the standard hydrogen electrode is much more cumbersome to deal with because you have to have a source of hydrogen gas, which would be some kind of a cylinder that you need to have, whereas the silver-silver chloride electrode and the calomel electrode are nice and compact. And they're commonly about the size of the redox probes that you used in lab, and they can also be much smaller. So if you do take chemistry 383 or 481, you will do some electrochemical measurements there, where electrodes are actually printed on a little chip. The silver-silver chloride electrode in that case is about the size of a pinhead. So the good thing about the silver-silver chloride electrode and the calomel electrode is that they are easily miniaturized and therefore portable. So if you want to take them to a field sample, you can easily take them where you want to and do your measurements, whereas the standard hydrogen electrode is much more cumbersome to deal with. So because each of these different electrodes have different potentials associated with them, you may need to convert from one to the other. So for example, if you take a measurement with the standard calomel electrode, what would that measurement look like if you use the silver-silver chloride electrode or if you use a standard hydrogen electrode? So this particular chart here you can find in your textbook, and it just shows you the conversion between each of those particular electrodes. So if the standard hydrogen electrode is at 0 volts, and you were to measure an iron 3+ iron 2+ solution, you would get a voltage of 0.750 volts if you use a standard hydrogen electrode. But if you use a silver-silver chloride electrode, you get a different voltage of 0.553 volts, and the difference between the standard hydrogen electrode and the silver-silver chloride is going to be this here, which turns out to be 0.197 volts. So using this chart, you should be able to convert between different reference electrodes, and you'll get a little bit of practice doing that on the worksheet. So that's all I have for this section. If you have any questions, please let me know.